So first of all, I'm going to share the PPT, which is the PPT of genetic algorithm. So now we have reached at a point where am I audible? Okay, fine. So now we have reached at a point where we are very much aware of, searching and optimizing some kind of solution, some kind of real-time solution. Like, can we give any example? Yes, there are real-time examples. Like, if you can follow a particular problem of robot path finding problems, right? So basically, what we can aim at that kind of problem, because we are going to set a kind of algorithm following which that particular robot must reach to its destination position from its starting position. So automatically there is one starting position and there is one goal position. Now you are, if you are going through this kind of, project or problem, you can easily find that robot may find two or three kinds of paths to reach at the destination. But sometimes it may happen that whenever the robot is utilizing a longer path, so automatically there the I mean the whole process must be very time consuming. So automatically there must be, the very much of computational cost as well, because you have to run your programs for a longer period of time. So basically, in that particular, scenario, what would be happen that maybe you require a kind of algorithm or a kind of a process so that this particular, robot can find the shortest minimum shortest path. So that is why it is called minimum shortest path algorithm. So now there are two ways. There are two ways. One way is being as a researcher, you can find out the particular minimum shortest path algorithm by computing the mathematical sums and mathematical, using some mathematical formulas. So you have to derive a long derivation, long formulas, long everything, and then after this mathematical process, the particular answer you have to feed to your robot or to your system, so that it can move along, along with your stated path or stated goal point. There is another approach, which is a soft computing approach. So that is that you can give your process or model or your robot to find the best possible solution optimally by optimally searching. So it has given the particular robot or particular model a freedom to, evaluate itself what can be the optimal solution. Optimal solution means the best possible solution for that particular problem. So now this is a kind of meta heuristic search. That means there is a search space which is a very large. We can say that is the universe of discourse, which we have already stated whenever we have done the fuzzy logic. Now we are shifting, we have completed the fuzzy logic and we are shifting in the evolutionary algorithm. And all of you know that, in the first class, when I have taken the introductory class of soft computing, I have mentioned that we have a number of evolutionary algorithm, right? Like genetic algorithm, which is here in the syllabus. Then we have differential evolution, we have particle swarm optimization. So all these are optimization techniques. The main funda of all the optimization techniques are to find a best possible solution, starting with a random generation of population, and automatically by searching or by evaluating itself, all the algorithms try to reach the best possible solution or the best fitted solution or the optimal solution. So automatically, whenever all the algorithms have been started from any particular random generation of population, those random generation population basically, comes from the universe of discourse. That means there is a very large search space. So you have to, I mean, you have to start with some particular point, and then you start evolving. I mean, you have to use all the search spaces, and you have to evolve yourself with the, with an aim to find the, I mean, the fittest solution. So now, coming to all the evolutionary algorithm, we have only genetic algorithm in our syllabus, which is the most simple one, which is the most primitive one, which is the first ever discovered evolutionary algorithm approach. So now, what is genetic algorithm? What I have just told, you can at least, follow through this particular, I mean, PPT, through this upcoming slides. That if you go through the slides of this genetic algorithm, then you are, you know, I mean, self equipped with the genetic algorithm idea, so that you can answer all the questions which may come to the may come in the semester. So I have prepared this particular slide in that way, because we cannot meet here. I don't know whether you can have that particular genetic algorithm book, which is who is the author of the, by the, I mean, Goldberg. I have once told in the class. I don't know how many of students can, access that particular, I mean, book, whether you have that book. So that is why, keeping that in mind, I have prepared this particular, slides in such a way that you can, once you can finish this particular, I mean, PPT, you can be able to answer the, I mean, questions regarding genetic algorithm. So, starting with the first slide. So, what is genetic algorithm? Genetic algorithm is a search technique that I have just told. So, basically, it is a particular search technique which is used to find the true or approximate solution to optimization and search problems. So, that is why we are saying that this is an optimization technique, this is a search technique. So, whenever a particular problem is given to you where you have to find out the better solution, we have to find out the optimal solution, or the most, suitable solution for that particular problem among many others. So then you will have to search and optimize this particular problem through some kind of phases. What are the phases, what are the stages, that we will come in the next slides. Now, this is categorized, this genetic algorithm is categorized as global search heuristic, because we have a global, search space from everywhere we can start to find our optimal solution. This is a particular class of evolutionary algorithms, because I have already told that there are many, many, many optimization techniques. GA is one of them. So this is a particular class which uses the techniques which is inspired by evolutionary biology. Now, this is a particular, the point where I want to know that how many of you can remember the biology class, which we have already taught in the class 11, 12, because, here we need to remember or recapitulate the gene mutation technology proposed by, we all of you know, the Darwin, the famous Darwin. So
That
basically, yes. So basically, this is a kind of evolutionary algorithm, and obviously the differential evolution, the genetic algorithm, all differential, all optimization technique or evolutionary algorithm technique, all are based on this gene mutation or the evolutionary biology, which basically involves the particular, steps like mutation, like selection, like crossover, like recombination. So I think all of you are aware of these steps, because these are the steps which we have already taught in our, when we are kids. So basically, now then, where is the difference between all these evolutionary techniques? Somewhere GA first, utilizes mutation, then maybe selection, then maybe crossover. In case of differential evolution, there you can find that the crossover will be first step, then mutation, then selection. That means this is a kind of, it is a kind of, trial and error method. It is kind of a mix and match method and the recombination method of all the evolutionary biology steps to form a particular, evolutionary algorithm process. And I mean, whenever you are going to follow all the evolutionary process, then you can find that any one evolutionary process may be suitable for a particular problem. Maybe it won't give you the optimal solution for the another problem. Maybe the second problem demands you to follow the second evolutionary problem. So there we have the need to follow all the evolutionary process whenever we are given a particular suitable problem, so that we can find whether the GA is suitable. I mean, whenever you are going to perform the research level work, then you need to understand that whenever the GA may give you the optimal solution, or maybe D will give you the optimal solution, or ant colony B optimization, or PSO, or which one. So this is what GA offers us. So this offers, a concept of evolutionary biology. Now, what is GA? That means the genetic algorithm includes a population of abstract representation. Now, I have already told that there must be a start process, there must be an end process, right? There must be a start step. Start step is the generation of random population. So this is the start state. And obviously, what is the end state? End state is whenever we have reached a particular, problem or particular solution, where when we will get our optimal solution or the fittest solution. So basically, that is why a population of abstract representation, this is the first step, this is the random generation population, which we often call as chromosomes or the genotype or the genome. So it has, different kinds of names. Then we have a candidate solutions. Candidate solutions are often called individuals, creatures, or phenotypes. And traditionally, all the solutions, we are talking about the solutions. So how we can represent the solutions? Solutions, every solutions can be represented in the binary value. Binary value. That means it is strings of zeros and ones. Usually this binary process, binary representation, are very much popular because our brain is very much active in recognizing all the zeros and ones bit streams. But obviously there are other encoding process as well. So what are those? I'm coming to the later slides. So basically, evolution, that means in case of genetic algorithm, this usually starts from a population of randomly generated, solutions, and that means individuals. And obviously, it will evolve, process. With each steps, with each process, or with each steps, and it basically, gives you the generations. That means if you can find out what our evolutionary biology was, that means obviously we have some parent, and obviously that parent reproduce some offspring. So here also, and obviously whenever a parent solution can produce the offspring, obviously we can say that our next generation has been arrived. So here also the concept is we should start with a randomly generated population, and automatically these individuals are getting evaluated by that those, four or three or four processes. That means the selection, that means the mutation, that means the crossover, that means the recombination. And by following those processes, we can generate our next offspring. That means we can create generations. So in each generation, now whenever your next generation has been has been arrived, then what to do? Then you need to evaluate the fitness of that particular generations. That means usually you can hear that some of our neighbors or some of our distant relatives, if they meet with us after several long times, that means maybe they have seen us whenever we are kid, and now whenever we have grown, so after certain long years back, they are again meeting with us. So it is very often you can hear this kind of statement that oh wow, your daughter is so grown up, your boy is so well grown, your son is so well grown up. So what does this mean? This means that there is a positive approach. There is a better feeling that our parents has raised us in such a beautiful manner that we are the better solution of them. We are like the replica of them, or we are the mirror image of them, or we are the better solution what basically a particular kid was. So basically what we need to understand is our parents are always doing this kind of, the process starting from our childhood to our, to at whenever, to at what age we have reached. That their concern is that so we can, that parents wanted to, every parents wanted to bring their child, to raise their child in such a way that they should be better than, I mean, them. So basically, what does this mean? What does this mean? That means every time each solution wants to create the next generation, which can be, which may be the fitter one, the better one, the better solution. So that is why in each generation, how can you evaluate whether your next generation is a fitter one or better one or not? That means you now need to evaluate the fitness of every individual which will be evolved in the next generation. Therefore you require one fitness function, right? And that fitness function must be individual and unique for every problem, every such problem. You, the researcher, have to decide, have to define the fitness function, which basically, evaluates the fitness of every individual in every population. And obviously multiple individuals are selected from the current population based on their fitness. That means if we can set a particular threshold that, I mean, above this particular threshold, we are going to take those solutions. We are going to mark them as the fitter one, as the better one. So we are going to take those, solutions. And obviously, beyond this particular threshold level, we don't, mark them as a fitter one. Maybe they are equal as as the current solution are, or the weaker one. So basically, in that particular case, we can, straight away take the previous solution. We are not going to take the current, the upcoming solution or the next generation solution if those solutions lie beyond the threshold value. So basically whenever we are going to extract the, fitter solutions, we can, the programmer can define whether he or she will be, will be going to, select only one fitter solution, the best one, or he or she can, select the, more than one, the certain multiple solution as well, who are basically, above the that threshold value. So based on that particular fitness value, so these populations, these new solutions are again, modified. So now we have already, after one generation, we have now got or received or obtained the new kind of solutions where we can have some of them are coming from the previous generation, some of them are evolved in the new generation. And how this modification can be happen? This modification can be happened by using that, sense of biology, which is the recombination process or mutation process and the crossover process to form a new population. Now, so new population, what we have now obtained. Now this is now the, ready to be used in the next iteration of the algorithm. That means again, whatever be the process we have followed for to create the first generation, that process is going to be repeated until we are getting the optimal solutions, or the algorithm enters if we can, if we have set a kind of number of iterations, in the beginning of the program. Let's say the programmer has set a kind of, number of iterations like 10,000. So if the program is running, for the 10,000 times, so automatically the program terminates, and it will be, declared that we have our optimal or fitter solution, and this is the most optimized solution. Or we can manually at least select that up to, I mean, this process can be continued till there is a manual speculation that whatever be the solution that now is coming, it will give you the fitter solution, or it will give you the almost, similar kind of solution which we have just obtained, I mean, from the very, previous generation. So in that particular point, when we are getting the curve like like a standard one, like a stable one, so there is nothing, not like there is no bigger change like in increasing or in decreasing any kind of. So then we can say that we can, I mean, we have achieved at the end of the particular algorithm. So if the algorithm has terminated due to the maximum number of generations, so maybe it may happen that satisfactory solution may or may not have reached. Suppose, let us take an example that I have told that maybe programmer can set a particular, number of iteration like 10,000. Suppose you are given I mean, a complicated program, much complicated program. Maybe you have to run your program like for 2000, I mean, 20,000 run, but you have already set the number of iteration is 10,000. So it may happen that after 10,000 iteration, you are losing the particular, I mean, new populations, which basically, which may, evolve after 10,000 to 20,000 iteration, because because the program is already stopped. So basically, you may lose the fitter one, you may lose the optimized solution in that case. So basically, there is a kind of, I mean, approach. There is a kind of, I mean, two kinds of, views that when we should terminate our program. So basically there are two ways, and as a programmer you need to, follow the trends of the, solution, and then you have to decide whether which one is better for your solution, I mean better for your problem, um, the, I mean, to set a maximum iteration, or you have to follow the manual trends. So now, coming to the key terms, what we have discussed so far, we have learned about some key terms which are very much associated with any kind of evolutionary algorithm. So obviously in genetic algorithm too, which is individual, which is any kind of possible solution. Population, which means group of all individuals. Now search space, that means all kind of possible solutions to the problem, which is a search space. We can start from anywhere. Chromosomes, which is a blueprint for an individual. Locus, the position of a gene on the chromosome, because we are talking about chromosomes, so automatically we know that chromosome involves gene. And genome is collection of all chromosomes for an individual. Now, coming to those key terms, these are kind of, theoretical approach. Now, how these particular key terms look like? So if you go through the next slide, you can see this is the kind of approach, and this is the kind of, I mean, the particulars which are being used as a bit string of zeros and ones, and or any other encoding part. That means now this is a kind of chromosome, right? This is a kind of chromosome, and if you can see the particular block, particular individual block, this is called gene. And these all the genes, I mean, this is a kind of called is genome. So this is a chromosome, genes, and genomes. So basically, what does this mean? Can you tell me what does this all this I mean blocks have put different kinds of colors, right? Some of them are similar colors. So what does this mean? This means that suppose a particular parent, suppose let us example that this is a particular parent. Let us say an example of me, fine. So suppose I have this kind of, I mean, I represent this kind of chromosome. So all these attributes, all these attributes represent my overall physical, mental, nature-wise attributes. That means um, my complexion, my height, my everything. I mean, my you know. Talking, I mean, manners of talking, or how I am calm or I am short tempered, I'm very much talkative, I am less talkative, I'm introvert, I am extrovert. Some kind of parameters are there in the chromosomes, right? So basically what happens that you have to, whenever we are going to produce the offsprings, whenever we are going to produce the offsprings, then basically what happens that these offsprings are that means the coming solutions are individually, independently mutate or crossover or selected in such kind of thing that particular offspring, extract some of my natures. So if that particular attributes appears in the offspring, you can see that your offspring has a kind of similarity for a particular attributes. Maybe your offspring can, maybe my offspring can look like me if he or she is going to take the looks attributes, or if she or he or my offspring is having I mean high, my kind of height, so that means a short height, you can see. So basically if she is going to extract the height attributes, then it is that kind of thing. Whether I am very much social, if she extracts this nature, this attributes, then obviously my offspring is kind of like this. So what basically, how you can define how your offspring will, I mean would be. So basically, it is a kind of mixture, because this offspring has the liberty, has the freedom to extract, the nature from his or her parents by its own. Some of kind of natures, my offspring may extract from me, may extract from my husband, and some kind of nature, it may be evolved during this mutation and crossover and recombination. So this is a very beautiful approach. This is a very fundamental concept of biology which is going to be followed in every algorithm. And in this manner we are getting you know next generation population, which may be better. Some of them are better, some of them are not. So we are going to take only the better one or fitter one or optimized solutions. Now what is genotype? So automatically we know that genotype is a particular set of genes in a genome, and phenotype is a physical characteristic. What is the smart, beautiful, healthy, etc., these kind of things. And automatically this is a kind of genetic disorder. Genetic, is there any kind of genetic disorder? You can hear sometimes, if you have doctors in your house, then you can see that whenever we are seeing a particular child or a particular person having certain kind of disability, certain kind of disorder, then doctors probably ask him or her that, do you have any history, medical history, or the family background to have this kind of disorder or disability. That means somewhere this particular disorder can be genetically. That means it comes from the heredity, or the background history. So this is genotype and phenotype. So automatically this is a kind of genotype, and obviously, and we are getting this kind of process when we are a particular solution in the next generation, it can extract this kind of thing. So basically it will get this kind of particular attributes, some of having this kind of attributes, some of having this kind of attributes. So basically by merging all these attributes, one particular chromosome has been formed. So now what is GA requirements? So GA requirements is particularly based on two major, counterparts. One is a genetic representation of the solution domain, and obviously a fitness function, which is going to help you to find out whether your solution is a fitter one or not. So basically, what could be the other representation? As I have already mentioned that we are very much, accustomed with this kind of, binary bit strings, but there are also other representations as well. These are the real numbers, permutation of elements, list of rules, program elements, genetic programming, any data structure kind of, representation, any of them. So now this is the fitness function. That means automatically we are starting a particularly randomly generated populations, right? So these are all the individuals. You can see we can have a n number of individuals, starting with the n number of individuals. This n can be 10, n can be 20, n can be 1 lakh as well. So depending on the problem and problem definition, and depending on the number of iterations we are going to assign, that means how much search run we are going to take. So automatically we need to have that much of population at the beginning, so that we can create offspring generation by generation in that manner. So if I take this kind of individual, so all the individuals must be fed into this fitness function, right? This is the programmer defined fitness function, as I have already told. So this fitness function evaluates, I mean, after this mutation, after this crossover, after this selection, this particular fitness function evaluates all the individuals and normalize, and you will obtain a kind of, new age population. There you can see that some of them, if these are the, number of individuals, you can see after it is evaluated by your fitness function, it may happen that your this hashtag 2, the second this individual becomes the first one, becomes a feature one, right? So basically this the last this hashtag in this population, this individual becomes the, better one, I mean the next one. But you can see that this hashtag n is being changed, right? But in case of, I mean, this particular thing, you can see there is no change. That means what? That means after getting evaluated by your fitness function, this n can be able to produce a fitter solution. So basically my algorithm is going to search and extract the fitter solution in each generation. So basically that is why now the hashtag n becomes the fitter one, not the previous one. But here, maybe this your hashtag 2 is going to evaluate it through this fitness function, and you can have the, I mean, after this evaluation process is over, you will obtain, not a very fitter function, I mean, fitter solution, maybe the weaker one, maybe the, I mean, the likewise. So in that case, you may, I mean, take the previous one which you have started with. So this is a kind of fitness function is evaluated. Now, basically my meeting time remaining is 1 minute 53 seconds. So basically I am going to end meeting here up to fitness function, and then again I'm going to connect for, I mean, starting with the basics of Genomes. So stay tuned.
Ma'am, I have a doubt.
Yes, yes. But okay, okay. Tell me, 1 minute
Ma'am, the fitness function will compute, will evaluate on n on basis on its previous value or the one it has evaluated into.
No, no, no. Based on this evaluated value, and also whatever be the fitness function you have written. That means suppose you have written a kind of, fitness function here, that it is going to get this value after the mutation, whatever this value, summation of the previous value and the muted value divided by 2. So this is a kind of, mathematical operation or mathematical formula. This is inside this fitness function. So this particular mathematical formula you are going to evaluate, right? So basically at that particular time, so basically you need the first one, the set of solution. And now after evaluating, that means after going through the mutation, after going through the selection, after going through the crossover, now you have obtained this particular solution. Maybe a fitter one, maybe a weaker one, maybe same like this.
Okay, thank you, ma'am.
Okay, now I'm going to, end this meeting, and obviously I'm going to again, start with the new one. I mean, after just give me 2 or 3 minutes so that I can start the new meeting.